look at this improper integral from 0 to infinity sin x over x in the x world. First, let me just tell you guys that this right here actually converges. And second, this is rather famous because none of the usual techniques that we know for integrations, such as integration by parts, u sub, or partial fraction, none of them will work for this right here. Third, I want to give a shout out to Zachary Lee because he was the one who showed me how to do this famous integral, alright? And he has this really cool math page. I will link the site to in my description. You guys should check it out, okay? And once again, Zachary is the man who showed me how to do this. And maybe he can tell you guys why this right here converges in the first place. And now, let's take a look on how this is going to work. And this technique is called the Feynman Technique. It's also called the differentiation under the integral sign. Okay, so let's take a look of sin x over x. The problem for this is that, well, we have this x on the denominator. If I don't have the x on the denominator, of course I can integrate sin x. That would be nice, right? How can I get rid of the x in the denominator? Well, how about if I can somehow multiply by x? I'm not talking about multiply the top and bottom by x. I'm just talking about multiply by x so that this x and that x can cancel out, right? That would be so cool, isn't it? But of course, I cannot just do that, otherwise I'll change the whole equation. But let me just write down the function part again right here. Let me just put down sin x over x like that. And this is how the Feynman technique works, all right? So we are going to introduce what we call a new parameter. And traditionally, we use b, but of course, you can use whichever letter that you would like, right? And let me put down the b right here. So I'm considering the function as sine of bx over x. If this is the function I have, well, to multiply by x, how can I produce that extra x? Let's take a look at this, and how about let's do the partial derivative with respect to b. How's that? Because I know if I'm looking at this in the b world, differentiate that, the bottom stays the same, and to differentiate sine bx, the derivative sine is cosine, and the input stays the same, which is bx. Now here's the chain rule part. We have to multiply by the derivative of bx in the b world. X is the constant, so we will have to multiply by x now. And as you can see, this x and that x will cancel, and we'll just left with cosine of bx. And that's wonderful. However, here's a problem. Originally, we have this sin x over x, and this is the improper integral going from 0 to infinity. So if somehow I change the integrand, I haven't integrated anything yet, you remember I still have to integrate this somehow from 0 to infinity, isn't it? And of course, if you have just cosine of whatever, this is not convergent anymore, unfortunately. But you guys have the idea that if I can somehow multiply by x by introducing a new parameter, somehow put it next to an x with a function, that's how we can multiply by this extra x, so that this x and that x will cancel each other out. That would be great. But this right here didn't work out nicely. Okay, let's go back and see what kind of things that we can possibly do to make this actually work out nicely, okay? So let me just consider this right here first. We have sine x, okay, over x, like that. And I'm not going to put on the b there, right there anymore because I know that it's not going to work. So let me just actually do like this, okay? So now, I would like to think about maybe I have to multiply by some function, and I will insert a b next to the input x, so that when I do the partial derivative, just like earlier, I can produce the extra x, so that that x and that x will cancel out. And now, just ask yourself, what are the functions that we know and that will work with sin x in terms of integration? Let me just give you guys an example. Would you like to multiply by ln x? And of course, as I said, I'm going to have the b right there, so that if I differentiate this with respect to b, I can multiply by the x, right? Well, imagine the x is no longer there. You have sin x and ln x, ln bx technically. Can we integrate that? No, unfortunately, right? When I say integrate, we have to make sure, can we integrate that in the x world as well? But no. Well, when we have sin x, I know a function that we can actually integrate with sin x, namely e to the something, right? So right here, I would like to multiply this function by e to the x. Let me just put this down for now, all right? And I'm going to keep track of what exactly I'm doing. I have to differentiate sometimes with respect to b, sometimes with respect to whatever, right? So, as you know, I'm going to put the b right here so that I can produce the x, and the x and x will cancel. Now, this is my new function. I will call this to be I of b. B is my input now, all right? B is my variable in this world, in the B world. And don't forget, we are still talking about integration. So we still have to integrate from 0 to infinity. And this is technically still in the x world. So if I define I of b to be this integral, and now b is the function, if you have studied Laplace transform, it's kind of similar, right? Because you have the L of whatever, and then the input was s, and you have that e to the whatever st, right? Negative st. S is the new variable that you end up with. But anyway, do you think this will work? Not quite, because if you look at the right-hand side, in the x world especially, this is not going to converge. Why? Because e to the bx, of course, that goes down to infinity. That dominates that part. But this is actually an easy fix, because all I need to do is multiply by negative. Right? Multiply by a negative right here, so that you know this actually will go down to the denominator, and when the e to the negative bx, when this moves to a denominator, when the exponential part is in the denominator, you can almost guarantee that it will be a convergent, right? That would be great. Okay, so this is my definition of I of b. Well, now, this right here, if you compare this and that, what's the difference? I have this new part, but I can pretend nothing happened, because I can say all I need to do is this is the same as saying integral from 0 to infinity sine x over x times e to the negative 0x. How's that? Because of course we know this is just 1, right? That's just 1. And now, you know, I put 0 right here. Well, what I'm saying is I just want to plug in I just have to plug in 0 into I, right? So plugging 0 into b, so I get I of 0. So the original question becomes that, which is the same as A. I just need to figure out what's I of 0, okay? However, the problem is that I cannot just plug in 0 right now, otherwise it defeats the whole purpose, because I will be just looking at that, right? Here is that part. I'm going to differentiate, integrate, and things like that. It's kind of like solving an exact differential equation if you have studied those already, because you have to differentiate and then go back to integrate and all that, right? It's really cool. First, we are going to be integrating this right here with respect to b. So let me just put that down right here for you guys. This is the definition of I of b. I will differentiate, well, technically, on the left-hand side, I had to put down the regular derivative, so I put down db, right? Because the left-hand side, I just have the b. And I will also do the same, because technically, on the right-hand side, this right here at the end is a function of b. So if you do that, you'll get a function of b. I will do db right here, okay? Okay, now let's use a different notation on the left-hand side. ddb of I of b, I will use the prime notation for derivative. So I'm talking about I prime of b. And now here is the cool part. I have an integral inside, and I differentiate the result of that integral. But I don't want that. I want to make the differentiation happen first, so that I can have the extra x, so that x and that x will cancel out. I'm going to bring this derivative into the integral sign, and this is that part called the differentiation under the integral sign. And what we are going to do is, we are going to use the Leibniz rule, all right? So I'm going to switch that. Now we will have the integral on our side from 0 to infinity. When I bring the derivative inside, look at the inside right here. We have two variables technically, namely the x and the b. So when we bring that inside, we have to talk about partial derivative. So I'll change notation to the partial with respect to b like this, okay? And right here, I will just write it down, sine x. And let me put this down on the top as well, e to the negative bx all over x, like that, right? And then this is dx, of course. Okay, this is what we have. From this step to this step, this is called Leibniz. Is the other guy besides Newton, right, for the calculus, Leibniz rule. And the whole process is called the Feynman Technique, all right? Anyway, let's work this inside out to see what we have. So on the left-hand side, we have I prime of b. And on the right-hand side, we still have the integral sign, of course, from 0 to infinity. And now check this out. The fraction box stays the same. The x is still on the bottom because we are differentiating with respect to b, right, the partial derivative. Sin x is a constant, it stays, so let's put that down, the sin x. And now e to the negative bx stays the same, right? But we have to multiply by the derivative of negative bx in the b world. Namely, x is the constant, so we have to multiply by what? Negative x. So I will multiply by negative x like this, right? And this is still dx. And now check this out. X and x cancel. Now that's what we have, right? Okay, let's take a look. We have this negative. Let me bring that outside. So we have the negative in the front. And this is the integral from 0 to infinity. Inside here, we just have sine x times e to the negative bx dx, all right? And on the left-hand side, we still have I prime of b, like that. Okay, I can fit a little bit more right here, so I will. I prime of b. This is equal to, the negative is still in the front, but I'm just going to put down the result of the integration right here for you guys, all right? Because this right here is actually doable because I have to integrate in the x world. B will be considered to be a constant for now, right? Let me tell you guys the answer for this, and if you want to know how to do this right here from scratch, you can check out the video in the description as well, okay? We need to use integration by parts, and the result is going to be, just for this part, okay? It will get negative e to the negative bx times cosine x plus b sine x over, I can put down over, b squared plus 1, like this, okay? And we're not going to put down plus c because, you know, this is going from 0 to infinity, and that was in the x world. So just indicate x go from 0 to x infinity, okay? Of course, this negative and that negative cancel to be positive. Now that's what we have. And now let's draw the continuation arrow, which also looks like an integral sign. That's so cool. On the left-hand side, we have I prime of b, so let's put that down. And on the right-hand side, I'm just going to say the following. I technically have to plug in infinity into all the x. Well, you know the dominating part is this, e to the negative bx, right? This is the dominating part because this is technically at most 1, likewise at most 1. So it doesn't really matter what this is. It's just at most 2, well, technically not, but it doesn't really matter at all. at most a constant, right? But this right here goes down to a denominator when x goes to infinity. And of course, we are talking about b is a positive value. If b is not positive, then this right here wouldn't converge in the first place. Because let's take a look. Right here, we have e to this negative already. And suppose b is also negative. Then you are talking about negative times negative, which is positive. And when x goes to infinity, then you know we will have e to the positive infinity power, and that will make the whole thing infinity, right? So we must have the condition that b right here has to be greater than or equal to 0, okay? In order for this to make sense. Anyway, just trust me that this right here is going to go to 0 when x goes to infinity, all right? And we have to subtract when x is equal to 0. But anyway, let me just write this down on this right here. I'll just say this is 0. This is when x goes to infinity, all right? And then we have to minus when x is equal to 0. I just have to plug in 0 into all the x. So we have e to the negative, well, let me just write it down just to show you guys I'm actually doing some work. Negative b times 0 like this times cosine of 0 and plus b times sine of 0, and this is over, over b squared plus 1, right? Okay, I prime of b, this is 0, this is negative, and this is 1, right? This is 0, this is 1, so we have negative 1 on the top. So we have negative 1 over b squared, negative 1 over b squared plus 1, right? Negative 1 over b squared plus 1. Okay, feel good so far? Now, this is not the function I of b anymore. This is the derivative of I of b. And remember, we differentiated with respect to b first. To get back to the original I of b, we have to integrate now. We have to integrate both sides with respect to what? B. So I will have to do db on both sides. And on the left-hand side, we'll just have I of b. And on the right-hand side, do it carefully. Yes, the integral of negative 1 over b squared plus 1 in the b world is just going to be negative inverse tangent. And the input is b, so I'll put this down right here. But you see that we have no number here. So be sure that because this is an indefinite integral, we have to put down a plus c, right? And now with this, we are almost done. Because remember, we are just pretty much looking for I of 0. And I just have to plug in b equal to 0 right here, b equal to 0 right here. But the problem is, I don't know what this c is. This is a close form for I of b, but I just really don't know what c is. So we have to go back to the board to see how else can we make a connection with this to somehow solve for c. Once again, this is the close form for I of b, but remember, we had our first original definition of I of b, which is right here, right? Originally, we defined it I of b to be the integral from 0 to infinity sine x over x times e to the negative bx dx, right? Well, this and that must have a connection. So I just have to look at this and will say set this equal to that integral from 0 to infinity, and we will have the sine x over x times e to the negative bx dx, right? And now look at, right here I have the b, here we have the b, of course, here we have the b. Now, I can just choose some b value, plug in. Hopefully, there's a good connection. Should I choose 0? No, because when I choose 0, this will be 0, and then we'll have c right here. And negative 0 times x and e to the that 0 power, we have 1. So this is pretty much just the original. Yes, in another word, this is going to be c when b is equal to 0. I still don't know what c is. So I'm going to choose another number besides 0. Okay, what other numbers can we choose though? Because this right here is a trouble. Remember, earlier at this stage, after we integrated, I had to plug in x equal to 0, right? And you see, when I plug in x equal to 0 in here, this exponential part is a dominating part, right? E to the negative bx, x goes to infinity, and this will make the whole thing equal to 0. Sine x, cosine x doesn't matter, okay? Well, why don't we do the same right here? This time, let b goes to infinity, all right? So right here, let me just write it down. I am going to let b goes to infinity. I'm going to write this down for you guys as follow. Right here, we'll first have negative inverse tangent. And let me just put infinity inside. Hopefully you guys don't mind this notation, all right? And then plus c, and this has to be the integral from 0 to infinity, and we will have sine x over x, and we will have multiplying this by e to the negative, b goes to infinity. Let me just put the infinity right here, okay? And then the x next to it, and then the dx. Can we figure this out? Negative inverse tangent of infinity. Yes, because this is pi over 2, and we just have negative pi over 2, right? So this is negative pi over 2. And then plus c. Okay, what's this on the right-hand side? Remember, e to the negative infinity for times x, and once again, x is just positive because we are talking about positive x equal to 0 to positive x goes to infinity, right? X is positive, right? I shouldn't say positive x goes to 0, but whatever. Anyway, this part is pretty much just going to be e to the negative infinity. You bring that down to the denominator, that will kill the whole integrand to be 0. So this whole thing right here, thanks to this part, okay, it will be just 0. And now when you integrate 0, you still get 0. There's no area. It doesn't really matter what this is anymore. So all in all, this part is just 0. Okay? Now, negative pi over 2 plus c is equal to 0. We know that c will be positive pi over 2. Haha! So finally, we know that I of b is equal to negative inverse tangent of b plus pi over 2 for the c. And remember, we were looking for I of 0, so that's this integral, right? Now let me just write it down properly for you guys. I of 0, it will be negative inverse tangent of 0 and then plus pi over 2. Of course, this is just going to be 0, so we have just pi over 2. Finally, let me write this down legitimately because this is such a famous question. And once again, pi pops out of nowhere, right? So let me write this down. Ladies and gentlemen, the integral from 0 to infinity sine x over x. No more e to the power because I'm looking for this, which is the same as I of 0. I will close that with dx. This right here is just positive pi over 2. Okay, this is the final result. Okay, this is so much fun, isn't it? Right? A lot of cool things that just happened right here. And once again, thanks to Zachary Lee, and he was the one who showed me this part right here. So be sure you guys check out his page. He has a lot of good math stuff over there. And hopefully you guys like my video as well. Share this video, subscribe. Thank you so much. And that's it.